So we have now seen the definition of this Nika covariance condition. And so basically the universal C-star algebra of the semigroup, quasi-lattice order semigroup, will be the universal one with respect to this Nika covariant representation. Not all representation of the semigroup, but restricted to this Nika covariance ones. And one of the major difference between these semigroup C-star algebra and the group C-star algebra is essentially this. You see the difference really comes from the fact that your representation is no longer unitary. Actually, it's actually far from a unitary. A lot of these Nika covariant condition will require that if two things have no common upper bound, then your range projection even have to be orthogonal. So there's no way that can be a unitary. So basically these kind of projections, they are kind of the major difference between your semigroup and your group. And it's not surprising, a lot of the information is actually contained in these projections. So let's just consider this is essentially the idea of the diagonal algebra, and I just want to give a brief introduction. And this is also related to this concept called the semigroup cross product. This is actually when Nika first studied these semigroup C-star algebras, he realized there has to be some kind of cross product structure. And then this is more clarified in a paper later on by Lacan and Rayburn. So I'm just going to go over this kind of background in this short lecture. So first of all, let's talk about the diagonal algebra. So let's consider the following. So if I consider the constant one function on the semigroup or the right principal ideal, basically, you can think about this as an element in the, let me do it this way. So you can think about this as an element inside the L infinity of P. Okay, so this is essentially a characteristic function on the right principal ideal. But the L infinity, you really can just imagine your L infinity as a subset of the bounded linear operator on L2 of P. It's essentially just by multiplication. But this one, if you treat it as a bounded linear operator on L2 of P, this is no other than the range projection. We saw it from last time. If you take the left regular representation, then lambda P, the range projection, basically project onto the span of everything inside the right principal ideal, and this is essentially just multiplying 1 on those basic vectors and 0 elsewhere. So this is the same as 1p. So this is you can think about this 1p is is an operator, and you can also think about it as a sub element in the L infinity. And the diagonal algebra is the diagonal algebra is essentially defined as the closed linear span of these 1p. Okay, so here let's just don't write the pp. Okay, that's just by 1p I denote lambda p star. So let me just pretend there's no p there. Okay, so this is for all p inside p. Okay, so this is called the diagonal algebra. And well, I need to justify why this is algebra. Well, first of all, when I define this, it just looks like a linear span. So algebra usually need to be closed under multiplication. That's essentially just what the Nika covariance is doing. So if you take 1p times 1q, then either that's going to be 0 or some 1 of r if r is equal to their least common upper bound, and if there's no common upper bound, then it's 0. So you take two 1p and 1q, you take their product, it's still inside these bunch of generators. So your d lambda is clearly an algebra. So that's why this is called the diagonal algebra. And this d lambda, you can treat it as a subset in the L infinity. It's going to be norm closed, and you treat the L infinity in the B of L2 of P. So it's a closed algebra, and because it's commutative, so this is commutative because 1p and 1q, all the generators, they commute. And then this is also unitable because the identity is essentially 1 of the identity. Okay, so that's basically constant 1 in the L infinity, and that's the identity in the B of L2. So it's a unitable, commutative, and of course it's closed under adjoint because all of these 1p are self-adjoint. So this is a C-star algebra, okay? A commutative C-star algebra is unit hole. So because it's a commutative C-star unit hole algebra, the basic Gelfand theory that tells you that this is just no other than so d lambda is isomorphic to the continuous functions on some kind of compact Hausdorff space. So here omega p is some compact Hausdorff space. And there's this omega p is actually has a name these days, so it's often called the Nika spectrum. Let's just write it down. I'm not going to characterize, I don't think I have time to characterize them, but there is a nice characterization of these omega p, okay? They can be defined in a certain way, certain subsets of your semigroup. So we actually have a notion of what they are actually. But in any case, all right, so let's first of all, let's briefly talk about this representations of these diagonal algebra. So let's do the following proposition. So first of all, if I have a representation of these diagonal algebra, let's say d lambda to some b of h, non-degenerate representation, then if you just let LP to be the pi of each of these 1p, well, then clearly because pi is a representation, then these LP, they're orthogonal projections, okay? Because, well, that should be quite clear because all the 1p are kind of orthogonal projections. And also the L of identity is equal to the identity operator, well, because it's non-degenerate. And also you have the LP, LQ, when you take the product, is equals to L of their least common upper bound. And so just usually the convention is that when PQ has no upper bound, in other words, their upper bound is infinity, you write it as a zero operator, okay? So that's just by convention, so I don't need to say PQ has a common upper bound, all right? And so this is one is basically fairly clear, but conversely, all such a family of projection actually give you a representation. So conversely, so all such family, let's say LP, P inside your semigroup, defines a representation, let's call it the pi L of your diagonal algebra, all right, on the whatever Hilbert space you're on. And you can also talk about when this pi L is faithful, in other words, injective. And in fact, this pi L is going to be a faithful representation of your d lambda. In other words, it's injective. That's even only if there's a very algebraic way of doing that. Okay, so this is for every z1 up to zn inside your p, and for some a that's strictly less than all these zi. And if you take the product of these projections, okay, you take LA minus L of zi, and here I going from 1 to n, right? That's going to be non-zero, okay? So sometimes this is called the properness condition, okay? The proper or jointly proper condition. All right, but anyway, so basically we have a very nice description of when these pi L is faithful on the diagonal algebra. So the proof, one is basically trivial, so let's just prove two. So for the second one, the idea is pretty simple, okay? So you just basically want to define your pi L to map one of x to the L of x, right? So let's just show that if you map pi L of 1x, you map it to the L of x is contractive, okay? So that's all you need to show. So once it's contractive, you can extend it to all the diagonal algebra. And to show that, there's actually, in other words, what you need to show is that if you take any typical element inside your, say, summation of, let's say, some alpha x, 1x, here x come from some finite set, you want to show this one, the norm of this one, in other words, you replace all the 1x by Lx, is less than equals to the norm inside the diagonal algebra, the alpha x 1x. Okay, so this norm, this is usually on the left hand side is a bunch of Lx, on the right hand side is a bunch of 1x. All right, so that's essentially what you need to do. And there's really a nice trick to compute a norm when your C-set algebra is generated by a bunch of these projections. So projections, if you think about it as an element inside C of x or C of omega, a projection is basically a characteristic function. Okay, so all of your 1 of x are basically some kind of characteristic functions. And essentially just asking a simple function, a linear span of these characteristic function, you want to have a norm estimate of how large they are. And well, how do you estimate the norm of a simple function is that, well, you write it as a summation of a bunch of characteristic function, but on disjoint subsets, okay? And you look at on each of these disjoint subsets, you look at the coefficient, and that will give you the sup norm. Now, which one is the biggest? It will give you the sup norm, and you compare that. Right, so this idea actually, if you, I know some of you took my measure theory from last term, and this is actually one of the idea I kind of hinted from last term when I talk about these simple functions. So you may want to compare this technique with what you have from last term. But the idea is the following. So I want to break this one as a basically a summation of some disjoint characteristic function, or in terms of projection, basically a pairwise orthogonal projection. So what I can do is the following. So I let for every subset A of f, okay, every f is finite, so for every subset of that, I define a projection. I define QAL is basically all the product of everything inside A. I take the product of the L of x. And for everything that's not inside A, I take their basically the complement, okay, 1 minus L of x. Okay, that's going to give me a projection. And one way of writing that as well, because Lx there, they need to satisfy this Nika covariant condition. So the first one is just equals to the least common upper bound of A, L of that, and you multiply the rest, okay? In other words, also you can write it as the product of everything x not inside A. You multiply the L of their these common upper bound inside, so you have LA multiplied by identity, and then you have LA multiplied by LX, which is just the least common upper bound of your A with the x. Okay, so you can also write it that way. But in any case, this QAL is kind of dividing your space into disjoint disjoint subsets. Okay, so what you have is that this is quite famous trick when you try to deal with this kind of semigroup diagonals, is that you take all these subsets A of this finite set and you sum up all this QAL, they're going to be equal to the identity. Okay, the proof is really simple. The proof is that your identity is just a product of all the Lx plus its complement, and everything here commute, so you expand this product, and each term basically corresponds to some of the QAL depending on basically some combinatorial argument. So this is fairly clear. And also you have your QAL, they are pairwise orthogonal to each other. Okay, this is just because if you have A and A prime, if they're different, then there's some element that's in one of the A but not in the other. Okay, and when you take their product, you have some factor of Lx in one and Lx complement in the other, and then you multiply to 0. So basically you have this nice decomposition. And moreover, each of these Lx you can write as the following. You can write as a summation of all those A which contains your x. Okay, so your x is fixed. A is a subset. You take all the subset that contains your x, and you sum up all these QAL. Okay, so essentially, now you can write your summation of alpha x Lx as the double summation. So here x is inside your finite subset. Each of these Lx you write it this way. So you write it as a summation over subsets of f, so that your x is inside A, and then you do the QAL. Okay, so that will sum up to the Lx. And now the nice thing is that, well, let's just rewrite this double summation. So I can say, well, I'm summing up over all the finite subsets. And then for each finite subset, well, what am I adding for the QAL is that whenever x is inside A, I need to sum up a copy of the coefficient alpha x, right? And so that's basically coefficient. And because all of these QAL, they're disjoint, okay, they're pairwise orthogonal. So you think about they act on pairwise orthogonal spaces. So this is really just if you write it as a matrix for each of these QAL correspond to a certain subspace. And this is basically a direct sum of them. And the norm of this operator is very easy to compute. This is essentially just a diagonal operator. And whichever this coefficient, whichever is the biggest, that's your norm, okay? But of course, that's only when your QAL is non-zero, okay? So this is essentially the supremum of among all these subsets. Of course, I need to require QAL is non-zero, okay? If it's non-zero, then I consider its coefficient. So this is x inside A, I take the alpha x. Of course, I need to do the absolute value, but that's essentially the supremum, okay? So now I have a nice description of how I can compute a sum of the alpha x, Lx. You think really just computing the subnorm of a L infinity or a simple function. And you basically do the same thing, okay? So if you let QA to be the QA of this constant, well, this 1, basically your generator for your diagonal algebra, you can do the same, okay? Do the same, and basically if you take a summation of your alpha x 1x, this is going to be the same sup of summation x inside A alpha x, but basically your QA here, you require QA is non-zero. So if you want to have the first supremum is less than equal to the second supremum, well, you're just essentially what you need to show is that if your QA is equal to 0, then QAL has to be equal to 0 as well. Okay, so suffices to show that if you have a QA is equal to 0, then this QAL is also equal to 0. In other words, if your QAL is non-zero, then QA has also to be non-zero. So the second one is always taking a sup over a larger subset, right? And to show that, let's suppose QA is equal to 0. So that just implies that if you take the product of x not inside A, you take the characteristic function on for basically the least common upper bound for A, and you minus that upper bound and take the least upper bound with the x, that's going to be equal to 0, okay? So basically I want to claim that one of these x has to be less than equals to your least upper bound of A, okay? That's the only thing happen. Well, if that happens, of course, you have these two are going to be equal, and then you have a 0 in your factor, so you get a 0. So let's assume that if you have your the least upper bound, let's just write this as A, so I don't need to write the least common upper bound of the set A all the time. So if I have something that's not equal to A, then if I consider this characteristic function at 1 with x, and if I do the 1a minus that, this is an L infinity function, first of all, and if I just look at what happens at A, well, because the A and x, their least common upper bound is not A, that has to be bigger than A, strictly bigger. So the second one will give me a 0, and the first one clearly give me a 1, so this is 1, which is non-zero. So in particular, this is not a 0 operator, okay, so this 1a minus 1 of A over x, that's not equal to 0, okay? That's for all the, if you have something that's not equal, right? So essentially, what do you come up with? Well, now if your QA is equal to 0, then what you must have is that there has to exist some x inside, well, not inside A, so that when you take x with least upper bound with the least upper bound of A, that has to equals to A, okay? Essentially, the reason is just really because this 1a, 1x is given by this Laplace representation, and then we have a pretty good idea what they are. But in any case, I have one of this is equals to that. And but if that happens, then this same thing will happen in terms of L as well, okay? So in this case, have L of the least common alpha bound of A has to be equals to the same thing. So that will imply the QAL is also equal to 0. Okay, so that basically finished the proof. And if you want to show the faithfulness condition, this is essentially the same proof. Okay, the faithfulness is that as long as you have that proper condition, all of these basically these conditions come from these kind of QAL. And so whenever you have something that's non-zero, then your L has to be something that's non-zero. Okay, so that's where it came from.